Hello all, and thank you for attending my dissertation defense. This talk will sum up the work I've done over the last 4 years in radar-based perception for visually degraded environments. Now, the overarching problem here is that an autonomous mobile robot must be able to build a model of its environment and localize itself within that model. In this video, we see a robot building an occupancy grid model of its world using LiDAR and localizing itself using visual inertial odometry. LiDAR and vision are commonly employed in solving localization, mapping, and higher-level perception problems. Depth cameras, GPS, and inertial measurement units are quite popular as well. Many of these can be used in single-sensor perception methods, and arbitrary combinations can be fused in multi-sensor methods. Methods based on these sensors often work beautifully when conditions are favorable, i.e. when the air is clear, ambient light is plentiful, and/or the robot has an unobstructed view of the sky. However, there are very few perception systems designed for less than optimal conditions, and none that are naturally suited to handle a broad range of perceptual challenges, as is demonstrated in this video. In the video, we can see a sensor platform with the same sensors, using the same perception methods, navigating the same environment we saw earlier, but now the environment is filled with a thick fog. We can see the state estimates from visual inertial odometry are much degraded due to the fog. Also, many of the measurements from the LiDAR sensor are backscattering from the fog rather than measurements of real objects. So the map has a lot of cells that are erroneously identified as occupied. These challenges aren't only found in lab spaces with fog machines either. From exploring subsurface caverns on the Moon, to navigating the dusty surface of Mars, or foggy environments like Venus and Titan, to exploring visually chaotic environments like the Comet 67P, autonomous robots deployed in a broad range of missions and environments face large obstacles from these and similar visual challenges. This is why my PhD research has focused on developing perception methods robust to these and other visually degraded environments. Now, my earlier work on visual inertial odometry for subterranean environments with no ambient light, which I presented at FSR in 2019, underscores the difficulties of perception in visually degraded environments, or VDEs for short. In an environment with no ambient light, a robot using visual inertial odometry must bring its own light source, but this violates a key assumption in visual odometry, that the illumination, and therefore the appearance of the scene, is constant and independent of the robot's state. When carrying an onboard light source, the appearance of the scene is now heavily dependent on the robot's pose within the scene. This results in many undesirable effects, which can cause the appearance of a visual landmark to change significantly between observations. This makes landmarks much more difficult to track as the robot's pose changes. Of course, if landmarks can't be tracked reliably, the odometry estimate's accuracy will suffer. So to address this, I created a custom stereo-visual front-end for OKViz that makes better use of the available information in an actively lit subterranean environment. It assumes the cameras will have overlapping visual fields, and it explicitly calculates the depth of detected key points using stereo triangulation. The system can then use key point depth as an additional source of information when associating new measurements to existing landmarks. This means my front end doesn't depend as heavily on key point descriptors for this task, so it's able to validate matches more reliably when a landmark's appearance may change between observations. When testing in actively lit subterranean conditions, I found the landmarks tracked by my front end were tracked for longer and were better distributed throughout the scene, and the odometry estimates accumulated significantly less translational drift as a result. However, this is very application-specific. For instance, when the brightness of the sensor rig's headlight was increased, my front end actually did slightly worse than the stock front end in OKViz. This shows how visual methods in visually degraded environments can require fine-tuning for very specific situations. One can imagine the result would have been totally different if the tunnels the robot was traversing were a bit wider, or if the camera used for VIO were upward-facing instead of forward-facing. This highlights the need for a more general solution to the problem of robotic perception and state estimation in visually degraded environments. I believe perception methods based on radar would fill this need. Radar doesn't require ambient light, and it's not affected by airborne obscurants like dust, smoke, and rain. Additionally, common frequency-modulated continuous wave, or FMCW radars, give range rate measurements for their detected targets, and this could potentially make dynamic obstacle detection much easier. The reality, however, is much more complicated, as this video shows. In the video, we can see aligned radar and LiDAR data from a sensor rig being hand-carried through a parking garage. Radar targets are represented as red points, and LiDAR targets are in green. The sensor rig's pose is marked by the RGB axes. It's immediately apparent that radar scans are very different from LiDAR scans. The radar scans are much more sparse, for one. There are at most 200 targets returned per radar scan, whereas the LiDAR returns tens of thousands. In addition, there's very little repeatability from scan to scan. The radar sensor may detect a target on a ceiling beam, a car, or a pillar, but the location of that detected target is not going to be consistent from scan to scan. Additionally, radar sensors tend to produce a high proportion of false positive detections. All of this should demonstrate the difficulty in using radar sensors for robotic perception. Now, the rest of my presentation will be organized as follows. First, I'll give a short primer on radar theory, so when I say something like range Doppler spectrum, we'll all still be on the same page. After that, I'll briefly review my projects from before my comprehensive exam. Luckily, we already covered visual inertial SLAM for subterranean environments, so there's just one other project left to cover. Then finally, we'll get into the projects and publications I completed since my comprehensive exam. Now, as shown in this figure, the radar measurement cycle starts when the radar's transmitter sends out a pulse of RF radiation with linearly increasing frequency, referred to as a chirp. Assuming there is a single point scatterer in the environment, the chirp reflects off that scatterer, and the reflection is detected by the radar's receiver as a time-shifted version of the transmitted chirp. The received chirp is then subtracted from the transmitted chirp to create an intermediate frequency, or IF signal. The frequency tau of that signal is proportional to the time of flight of the chirp. If there is only one scatterer in the sensor's field of view, determining the frequency of that signal would be trivial, but in the real world there's going to be a huge number of scatterers, and we want to identify the contributions of all of them to that received signal. So to do this, we take the Fourier transform of the IF signal to convert from the frequency time domain to the power frequency domain. The largest peaks in that Fourier transform correspond to the strongest scatterers in the environment. Now, in application, we can't perform a continuous Fourier transform on the IF signal. Instead, we need to digitize the signal by sampling it with an analog to digital converter, or ADC. These samples are then arranged into a radar data array, depicted here with each box representing an ADC sample. We can then perform a fast Fourier transform, which is a type of discrete Fourier transform, across the array, resulting in a 1D profile of the received power at a discrete set of ranges from the sensor. This can be represented using a heat map, such as the one shown here. In frequency-modulated continuous wave radars, the process I just described is repeated many times for a single measurement, and the radar data arrays from each chirp are stacked to form a 2D radar data matrix. After performing the FFT across each row, there's going to be a difference in phase between the signals in each column proportional to the range rate of the obstacle in that range bin. We can then perform a second FFT across the columns of the data matrix to create a profile of the power of the signal received by the sensor in range and range rate, also referred to as the range Doppler spectrum. This is often represented as a 2D heat map, such as the one shown here. Notice this clear peak in intensity indicates we have a strong radar reflector at 11 meters from the sensor, with range decreasing at 0.8 meters per second. Most commercially available radar sensors will implement a third processing step. They segment out the strongest detections and ignore the lower power signals, which are more likely to correspond to thermal noise, or so-called clutter. This is usually done with a constant false alarm rate detector, which identifies the strongest peaks in the range Doppler spectrum. These detected peaks are returned to the user as a set of point targets parameterized by their range, range rate, and intensity, and the rest of the information is discarded. Now, the radar sensors used in my research use this process to detect targets, but they also use phase differences in the returns between multiple antennas to estimate the angle of arrival of those detected targets. But I'll save the discussion of angle arrival estimation for a little bit later. Now that we have that important background, I can briefly review my first successful foray into radar-based state estimation, which I presented at ICRA in 2020, estimating the velocity of a sensor platform using radar Doppler and inertial measurements. Now, previous methods for radar-based state estimation were limited to a 2D environment, and they also often relied on heavy and power-hungry radar sensors, such as the one pictured here. This makes these methods unsuitable for small, agile robots, such as micro-aerial vehicles. My work, on the other hand, it uses a lightweight, low-power radar on a chip and an IMU, which are both easily carried by an MAV. Now, my radar sensor uses the signal processing and target detection process I just described to return targets parameterized by their range, Doppler velocity, and their azimuth and elevation angles. If we assume the sensor platform is moving, and all objects in the scene are stationary, then the velocity of objects in the scene relative to the sensor has equal magnitude and opposite direction to the velocity of the sensor platform. An object's Doppler measurement is then the projection of its relative velocity vector onto the ray between the sensor and target. If we have Doppler measurements of many objects distributed throughout the scene, then we should be able to regress the velocity of the sensor platform. This is reflected by my Doppler sensor model, where the true radial velocity of a target is the dot product of the local frame velocity of the sensor and the unit ray between the sensor and target. Now, it's possible to use this model alone to estimate the sensor platform's local frame velocity, but there's actually a large amount of noise in the Doppler measurements, which makes estimates from the Doppler error alone unreliable. So I jointly estimate the system state at several time steps using IMU measurements to constrain the change between adjacent states, as shown in this factor graph representation of my system. The state vector includes the sensor's local frame velocity, attitude, and IMU biases. I estimate these states by minimizing the cost function shown here over a sliding window of k successive Doppler measurements. I compared my radar inertial method to visual inertial odometry and LiDAR odometry using motion capture for ground truth. These plots show typical errors in the velocity estimates for all methods, and it's clear from these plots that the accuracy of my radar inertial method's velocity estimates are on par with other state-of-the-art methods. This brings us to my first project that was published since my comprehensive exam, radar inertial state estimation and obstacle detection for micro-aerial vehicles in dense fog. This work was published at ICER in 2020, and additionally, the state estimation component of the work is incorporated in the robust navigation module of the Jet Propulsion Laboratory's Nebula system for autonomy in challenging environments. Nebula was recently accepted for publication in the Journal of Field Robotics and is currently being studied for autonomy in space applications, including exploring Martian caverns and the lunar surface. For state estimation, I use a refinement on the radar inertial estimator I presented at ICRA. The biggest change, though, is that I now estimate velocities in the global frame rather than the sensor frame. Also, I no longer simply drop states and measurements when they pass out of the estimator's sliding window. Instead, I linearize their error terms and collect them into a single marginalization error term using the Schur complement method. The Doppler error term has changed as well, and this is related to a change in the sensor model. The updated sensor model now reflects that we're estimating velocities in the world frame, but more importantly, it also explicitly includes the error in the sensor to target ray. This is why the Doppler error term now includes the error in the target ray in addition to the Doppler measurement error. This is because, unlike with LiDAR, there are likely to be significant errors in that target ray. And in this case, the target ray error is both a state to be estimated and an error to be minimized. These updates improve the stability and accuracy of estimates from my radar inertial state estimator to the point where it could be used in closed-loop control of an MAV, as demonstrated in this video made by Shakib Ahmad. Now, although the MAV state estimate is clearly not perfect, it is able to hover in place with it for at least a short time with minimal drift using only state estimates from the radar inertial state estimator. The second component of this project is the use of radar for obstacle detections. Occupancy mapping is commonly used for obstacle detection, but using radar with occupancy maps comes with significant challenges. First, commonly available occupancy mapping packages, such as Octomap, assume a beam sensor model. In this case, rays are cast from the sensor to each point in a scan, and the occupancy probability for a cell is decreased if it's traversed by a ray and increased if it contains an endpoint of a ray. This is a problem for radar because radar doesn't cast a discrete set of rays, and multiple targets might be detected along the same ray. So to address this, I modified the ROS Octomap package with a volumetric sensor model that better represents the function of a radar sensor. In this model, occupancy probability is increased for cells that contain radar returns and decreased for all other cells within the sensor's field of view. Now, this video shows a radar-based Octomap using the new sensor model with LiDAR scans for reference, and it demonstrates the principal remaining difficulty in using radar scans in occupancy maps. Radar scans contain a relatively high number of spurious returns, so we can't be very confident an individual radar return actually represents occupied space. This means the map just isn't very reliable. Some obstacles that are visible in the LiDAR scans are captured in the map, but others, like this pillar coming in from the right, go completely unnoticed. In order to assign greater confidence to the radar points being fed into the occupancy map, we need to discriminate between true returns and noise. This is why I developed a learned noise filter for radar point clouds. It uses the point net segmentation network to identify the points in a radar scan that correspond to noise and which are true returns. This video demonstrates the weekly supervised training procedure I used. First, we can see radar points in red aligned with LiDAR points in green. Radar points that are within a threshold distance of the nearest LiDAR point are labeled as keep, and all others are labeled as discard. Next, we can see the labeled radar points with keep points in green and discard points in red. These labeled point clouds are what is actually used to train the point net segmentation network. Now, this video shows the same data set we saw previously, using the same mapping method, but with the addition of the learned noise filter. We can see right away the map is far denser. It persists after the sensor moves away, it captures the floor and ceiling fairly reliably, and it also reliably captures salient obstacles like this car on the right, the pillar coming in on the right as well that was missed in the previous mapping method is well represented in this map. This is clearly a huge improvement over the original method. This video demonstrates my full radar state estimation and mapping pipeline in use. The sensor pose is estimated by integrating velocity and orientation estimates from the radar inertial state estimator. We can also see raw returns projected onto the image stream from an onboard camera, and motion primitives evaluated by a simple local planner. And we can see the radar inertial state estimates are quite sufficient for local relative motion estimation at least, and the obstacle detections reliably represent walls, door alcoves, and other salient features of the environment. And because both the state estimation and mapping method are radar-based, they're not affected by smoke and fog. So this system could be used to aid a small, agile robot in navigating such visually degraded conditions. Now, up to this point, my work has used the point clouds of targets generated on board various automotive radar sensors. This work was fruitful, but the signal processing and target detection systems implemented on board the sensors I've used is far from ideal for robotic sensing applications. And this isn't just my problem. It applies to nearly all of the automotive-type radar sensors currently used in robotics research. The signal processing and target detection algorithms used by automotive sensors are designed to answer easy questions like, what is the range to the car in front of me? But they're generally inadequate for more difficult questions like, what are the 3D locations of trackable landmarks in this scene? So this problem wasn't just holding back my work, it was impeding radar research in robotics generally. Many of the most successful robotic perception methods using radar do not use point targets as input. Instead, they use dense, high-resolution radar images like this one. However, the sensors used to create these images are large, power-hungry, and strictly two-dimensional. My goal was to find a way to create dense radar images analogous to this one, but with 3 dimensions instead of 2. In theory, I could create 3D radar images using the automotive sensors I already had. I would just need to gain access to their raw ADC samples so I could bypass the sensor's onboard signal processing and implement my own on a host computer. However, the sensor doesn't provide a means to stream these samples in real time. Additionally, the sensor's antenna array is a bit of a problem. Note, in this image, each of these is a single antenna. The sensor has 4 receivers and 3 transmitters, and this relatively small array severely limits its angular resolution. This is why I decided to add another sensor to my arsenal, an imaging radar with 4 times the number of antennas and therefore much better angular resolution. In this image, each of these is a single antenna, and one can see here that the imaging sensor has a much larger antenna array, but like the smaller sensor, the imaging radar doesn't provide any means to stream raw ADC samples in real time. The smaller automotive sensor actually can stream live ADC samples to a separate data capture board via an LVDS connection, but this board only supports logging and after-the-fact processing using TI's Windows-based software. This makes it extremely difficult to sync raw radar data with other sensors, and impossible to use the sensor for real-time applications. But through careful reading of the data capture board's datasheet and sleuthing its Ethernet communication protocol with Wireshark, I was able to write a ROS node that sends a series of command packets that essentially trick the capture board into live streaming raw ADC data over Ethernet. The ROS node then reads this ADC data from each packet, reassembles it into complete data cubes, then publishes each data cube in a custom message type. The imaging sensor was more difficult. By default, it only supports logging ADC data to an onboard solid-state drive, and once again, communication is only supported using TI's Windows-based software. However, the sensor requires a separate driver board, which does have an Ethernet port. So, once more, careful reading of the datasheets and lots of Googling offered a potential solution. I found the driver board is capable of running an RTOS from its micro SD card. TI provides source code for an RTOS that supports an older version of this sensor as part of its Vision SDK. With this source code, I was able to patch together support for the newer sensor, then write a new program that live streams ADC data via the sensor's Ethernet port rather than saving it to the solid-state drive. The ADC data packets are then decoded and published as datacube messages by another custom ROS node. My method for processing these raw signals takes advantage of the sensor's multiple input, multiple output, or MIMO architecture. A MIMO sensor has multiple transmitters and multiple receivers, we'll say N transmitters and M receivers. The signals transmitted by the transmit antennas, phi sub n of t, are orthogonal, which in this case means the cross-correlation between any two of the transmitted signals is 0. The transmitted signals combine and are reflected off objects in the environment, and the reflected signals are received as y sub m of t by each receiver. But because the transmitted signals were orthogonal, the received signals can be split back into the components caused by each transmitted signal, y sub mn of t. So for each set of transmitted signals, we get n times m received signals. Further, because the transmit and receive antennas are spatially separated, there's going to be a difference in the phase of the received signals for each transmit-receive pair that's dependent on the angle of arrival of that signal. If we organize the range Doppler processed signals from each transmit-receive pair into a 4D data cube, we can perform Fourier transforms across the antenna pair dimensions of the data cube to create a plot of the received power in range Doppler and angle of arrival. This can be interpreted as a dense 4D image in range, Doppler, azimuth, and elevation. And this is a resource-intensive process, though, requiring multiple fast Fourier transforms over up to 5.5 million complex values for each frame of the imaging sensor. When done serially on a CPU, it takes an unacceptable amount of time. Fortunately, the process is highly parallelizable. I implemented this signal processing pipeline to run on a GPU using the CUFFT package and several custom CUDA kernels, and now processing each frame takes a mere 5 milliseconds on my laptop's GTX 1050. I armed two of my lab mates, Kyle Harlow and Arpit Savarkar, with these new tools and the sensor rig pictured here, and they helped to gather a new publicly available robotics dataset focused on radar-based state estimation and mapping. It includes over 2 hours of data with dense radar measurements, LiDAR, and inertial measurements, as well as highly accurate ground truth poses. The upfront costs to just develop the capability to gather this data were quite significant, as I just described. It amounted to several months of work on my part. But now that barrier to entry is removed, and any researcher can develop their own methods using 3D imaging radar, I'd like to show a few animated examples from the dataset in various environments, starting with an indoor built environment, the University of Colorado's Engineering Center. Here we can see points from the LiDAR sensor in white, and scans from the imaging radar are shown as a 2D heat map where red represents lower intensity readings and violet represents higher intensity. I should emphasize the heat maps in the dataset are three-dimensional, but only 2 dimensions are shown here for ease of interpretation. We can see that intensity peaks in the radar images clearly correspond to features in the environment. And crucially, these intensity peaks are repeatable over changes in the sensor rig's pose, meaning they could be tracked to estimate the pose of the sensor rig. We can also see coming up that the sensor is capable of resolving multiple closely spaced features in the environment. For instance, these aluminum window frames are clearly resolved with distinct peaks in the radar image. Our second example is an outdoor multi-use path. In this environment, the sensor rig is carried on an electric skateboard, providing speeds of up to 7 meters per second. Now we can see the sensor is able to clearly detect static obstacles like trees and fences, in addition to dynamic obstacles like pedestrians and this cyclist who's coming up on the right. I'd also like to highlight here another advantage of the color radar dataset over existing radar datasets. The color radar dataset includes the raw ADC samples from every radar scan in addition to these 3D heat maps. Other publicly available radar datasets use the signal processing and target detection methods implemented on board their sensors, and as we've discussed, these methods are usually designed for advanced driver assistance and are pretty ill-adapted for robotics work as a result. Our inclusion of raw ADC samples gives users the freedom to develop their own processing algorithms specifically suited to their applications. Our last example is in a subterranean environment. It's a former gold and silver mine that now serves as an educational facility for the Colorado School of Mines. We can see the rock walls of the mine are clearly resolved in the radar images, potentially providing a good reference for odometry and mapping. And additionally, other objects like vehicles and equipment are visible in the radar images as well. I also developed an end-to-end learned method to estimate the relative pose change of the sensor between images in the color radar dataset to demonstrate the dataset's use and its applicability. This method could be a jumping-off point to develop a learned radar pose constraint to be used in a radar-based odometry system. Now, the radar images in the color radar dataset are given in spherical polar coordinates. This image is a 2D slice in the range azimuth plane of an example image from the dataset. I'm trying to estimate relative poses in Cartesian coordinates, though, so I resample these polar images to Cartesian coordinates using trilinear interpolation. Here we see a 2D slice in the XY plane of the same image after resampling. To create an input for the learned model, we take a pair of these resampled 3D images and stack them along the channel dimension. This leaves us with a 3D 2-channel image, where channel 0 is the amplitudes of the image at time 0, and channel 1 is the amplitudes of the image at time 1. The stacked 3D images are then fed into a convolutional neural network model whose architecture you may recognize because it's inspired by VGG13. It consists of 5 blocks of 2 3D convolutional layers, each with a kernel size of 3 and strident padding of 1, so their output is the same size as their input. Each block of convolutional layers is followed by a max pooling that halves the size of its input. The output of the last max pooling layer is fed into 3 fully connected layers, and the last of these has 6 outputs and no activation function in order to regress the 6 degree of freedom pose change between the 2 stacked input images. The network is trained using the objective function pictured here. The optimal network parameters are those that minimize the mean of the weighted sum of the squared errors between the ground truth and estimated translations and the ground truth and estimated rotations. The model was trained using the atom optimizer over 25 epochs, and the learning rate started at 10 to the negative fifth and was reduced by a factor of 10 when the validation loss plateaued. To create training and testing datasets, we find every possible pairing between measurements from the imaging radar and the color radar dataset satisfying two conditions. Paired images must be from the same sequence, and to ensure there's significant pose change between paired images while maintaining some overlap, the delta t between paired images must be between 0.4 and 1 seconds. This results in a dataset of around 250,000 examples, of which we use a randomly selected 80% for training and the other 20% for evaluation. This slide gives some statistics on the errors in the poses estimated by the LEARN model, as well as the ground truth pose changes in the dataset. The upper table gives stats on the ground truth pose changes, and we can see the greatest translations between pairs in the dataset are in the x dimension, and the greatest rotations are in yaw, or about the z-axis. But there are significant changes in all dimensions. The lower table gives stats on the errors in pose changes estimated by the learned model. We can see the mean errors are low relative to the mean ground truth pose changes. Also, the errors are highest in the x and yaw dimensions, but if we consider error as a percentage of the ground truth pose change, the x and yaw errors are actually the lowest. This is demonstrated here by these cumulative error histograms for the estimated relative poses as a percentage of the ground truth relative pose in each dimension. We can see the LEARN model is able to regress poses with 10% error or better in any dimension at least 95% of the time. Further, the LEARN model is able to regress poses with 3% error or better in any dimension around 90% of the time. In some dimensions, the performance is even better. The LEARN model is able to predict translation in X with 1% accuracy or better 90% of the time, and rotation about the Z-axis with 1% accuracy or better 75% of the time. All of this shows the LEARN model is able to accurately regress 6 degrees of freedom relative poses between 3D radar images from the color radar dataset. This slide shows activation maps from the first 3 blocks in the convolutional section of the LEARN model on the right, and the input image pair that caused those activations on the left. The input images are presented as heat maps, as we've seen before, and the activation maps on the right have undergone principal component analysis to reduce their channel dimension to 3 so that they can be viewed as RGB images. Also, all of the images shown here are 2D slices of 3D images in the XY plane. Now, it's easy to recognize features in the first activation map that correspond to features in the 2 input images, as we can see here and here. As these features pass through additional convolutional and max pooling layers, we can see how they're slowly reduced to a small number of blobs, which the fully connected section then associates to estimate the relative pose change between the 2 images. This demonstrates the convolutional section has learned to detect repeatable, matchable features in the input radar images. This could likely be extended to create a learned key point detector for 3D radar images, which would allow for the tracking of radar landmarks across many images to help create a 6 degrees of freedom radar odometry system. So to summarize, this work presents encouraging results in 6 degrees of freedom relative pose estimation using dense 3D radar images, but more importantly, it demonstrates the vast untapped potential in using these 3D images for robotic sensing. The fact that it's possible to detect and match stable, repeatable features in 3D radar images raises a multitude of possibilities for this exciting new sensing modality. 3D radar imaging has the potential to facilitate huge advancements for state estimation and perception for small, agile robots operating in 3-dimensional environments with a broad range of perceptual challenges, and I believe we've just scratched the surface of this potential. I hope all of these projects, taken together, give you an idea of the great and mostly untapped potential in the use of radar for robotic perception and state estimation. I also hope these projects show that the work I've undertaken over the course of my PhD has advanced the state of the art significantly, and that, thanks in some small part to my contributions, Radar is now a more useful and accessible mode of robotic perception than it was just 4 years ago. Thank you so much for your time and attention. I hope you found my talk interesting and useful. I'd like to thank my advisor, Chris, my lab mates in the ARPG, my collaborators at NASA for their help and support throughout my PhD. And lastly, I want to thank NASA itself for supporting my research through the Space Technology Research Fellowship. Thank you so much.